This video is about gauge wave theory and quantum lens technology. Here you will discover how gauge wave theory might explain quantum mechanics, gravity, dark energy, and galactic rotation curves. You will also learn about the quantum lens, which is a new scientific instrument that can detect gauge waves. To develop this technology, we have set up a company called Type 1 Systems, and we are currently seeking pre-seed funding, and we are offering 8% equity at this point. Contact us if you want to invest. This video is an entry for the Core 1 competition, an initiative by the Theories of Everything YouTube channel, and I will also be submitting it to Summer of Math Exposition 5 by the 3 Blue 1 Brown channel. Before we dive into the mathematics, let's take a look at two conceptual models that help us understand quantum mechanics a little. The first one is the bouncing oil droplet experiment. It is made by taking a bath of silicon oil and put it on a vibrating platform, and then you can get small droplets of silicon oil to bounce on the surface. Here it is important to look at the two waves, the one coming from the vibration of the bath and one wave comes from the impact of the droplet on the surface. The interaction of those two waves made this system show similar characteristics of a quantum system, and we can reproduce known quantum experiments like the double slit experiment, the tunneling effect, and many more with this system. The second model was made in 1966 by Edward Nelson. He considered a particle influenced by Brownian motion, and from that he was able to derive Schrödinger's equation. This approach was later known as stochastic mechanics, and the extra momentum the particle get from the environment is known as osmotic momentum. Here we can see an illustration, a particle that is moving under the influence of the environment, and the yellow dot is the particle and the blue dots are measurement. In stochastic mechanics, the wave function is not something physical, it's just a stochastic description of the particle state. This makes it easy to understand why the wave function collapses when you determine its state with a measurement, and it how spreads again after the measurement. So this gives the idea that the probability in quantum mechanics comes from interaction with the environment and not fundamental to nature as in the Copenhagen interpretation. To quickly show the relation Edward Nelson found, we will do it in the opposite way. So we will start from Schrödinger equation and end with coupled impulse equations. We start by writing up the wave function as an exponential function in a complex number, and then we split the complex number in the real part and the imaginary part. We can express the canonical momentum as the gradient on the imaginary part and the osmotic momentum as the gradient on the real part. Then we write up the Schrödinger equation, and then we put in the expression for the wave function. Then we differentiate the terms, we then factor out the wave function, and then we take the gradient on both sides. And finally, we can put in the expression for the momenta and split it in the real part and the imaginary part. And then we get two coupled impulse equations as a result. In his 1966 article, Edward Nelson started by finding the impulse equations and worked his way up to the Schrödinger equation. When we calculate a quantity in quantum mechanics, we normally take an average over some operator. So if we put Schrödinger equations into the average, we can see that the Schrödinger equation is actually an average energy equation which averages to zero. This means that the osmotic influence is balanced, so as much energy is flowing in as is flowing out. The uncertainty relations give us an estimate on how the energy and the time scale is related in this balance. The next tool we need is generalized electrodynamics. We start with the normal electrodynamics definitions. Rho is the charge density, J is the current density, phi is the electric potential, A is the magnetic vector potential. All of our calculations are in Gaussian units, and I don't include material constants. Then the electric field E is defined as minus the gradient on phi minus the time derivative of A, and the magnetic field B is defined as the rotation on A. I'm now showing how the field equation is derived. We start by writing up the wave equation in the electric potential as the identity. Then we start with the left side and using the definition of the potential and differentiate in under the integral. A lot of terms cancel out and we end up with the charge density. Then on the right side, we use the definition of the fields to isolate gradient of phi and insert it in. After a rewrite, we have the first field equation. Then you can do similar steps with the vector potential, and that gives us the second field equation. And now we can see that we have a common term in the two equations. Often that is set to zero, but in generalized electrodynamics, it's used to define a new scalar field component I call the electric time component. And then, of course, we can get the two last by taking the divergent on the magnetic field definition and the rotation on the definition of the electric field. Charge conservation is something that is normally observed in experiments. Here we write up charge conservation and rewrite it using generalized electrodynamics. We insert the expression and then we cancel out and collect, and then we can remove the constant first. Then we get a standing wave equation in the new field component. We started with charge conservation, and instead of zero, we end up with this standing wave. An idea I got was, what if we describe a charged particle, like an electron, as a standing wave in this new field component? Standing wave solutions is something well known in science, and if we write up the solution in spherical coordinates, they factor out as four functions of each of the coordinates. So the r is spherical Bessel functions, the first angle is associated Legendre polynomials, the next angle is just a linear combination of cosine and sinus, and the last is again a linear combination of cosine and sinus. There is of course some extra constants that need to be determined by boundary conditions. If we take the simplest solution to the wave equation, the angular dependency goes out, and we just have a function of time and radius. So here I've tried to visualize the wave. There are still some artifacts I was not able to remove, where the surfaces get cut off by the bounding box. But we can see that it oscillates between the blue and the red, where the blue is the positive and red is the negative values. So let's just enjoy it a little. A gauge function is a function that can be added to the electromagnetic potentials without it changing the fields. So when it is added to the electric potential as minus the time derivative and to the vector potential as the gradient, we can write up the electric and magnetic field and substitute in the gauge expressions, then the terms cancel out and we get zero. When we put it into the expression for the time component, we get a standing wave in the gauge function, and the time component works as a source for this wave. So when the electric time component goes from minus to plus, it goes from sending to receiving gauge waves. To explain quantum mechanics from gauge waves, we first look at the particle wave. If we integrate the particle wave over space, we can average out the space dependencies. We get that the particle is swinging as a cosine of time. This means that the particle wave is periodical in sending mode and receiving mode and in a balanced way, so as much energy is received as is sent out. This is similar to what we saw with Schrödinger's equation earlier on. The two interacting waves also remind us of the oil droplet experiment. Now, to get a little away from the math, here is a simulation showing how a quantum particle starts at zero, slowly starting to wobble and move under the influence of gauge waves. Very similar to Edward Nelson's interpretation of quantum mechanics. Next, if two particle waves are close to each other, they will screen each other from gauge waves in the other one's direction, meaning that there will be a net force pulling them together. And this screening effect can be the cause for gravity. That would give us gravity acceleration that is proportional to the gradient of the electric time component or minus the gradient on the radiation field of the gauge waves. The next thing we could explain with gauge waves is dark energy, because when we have an energy density of gauge waves, it adds an extra contribution to the diagonal of the stress energy tensor in general relativity. So we might be able to remove the cosmological constant and explain that with energy density of gauge waves. I am sure that would make Einstein happy. When astronomers started to observe galaxies, we have noticed that they were spinning too fast to be held together by Newtonian gravity, and different explanations came up. The most known is dark matter, but there's also another explanation called modified Newtonian dynamics that says that there is a change to the way gravity works at bigger distances. This article was published in Journal of Physical Communication, and in that they have a model where a photon is radiated between atoms on a continual basis or global basis. From that model, they can show that they get a modification to the normal gravity, and they are able to find a bigger acceleration that explains the galactic rotation curves. But the problem is that we have not observed those photon transmissions even with our big telescopes. So gauge wave theory suggests that this photon transmission between atoms in the model should be substituted with gauge waves transmission between fundamental particles. And that should give the same effect and therefore explain galactic rotation curves in a modified Newtonian dynamics type of way. To understand the quantum lens, we start by writing up the wave equation for the electric and magnetic field. Then we get something like this. If we then look for space where there is no charge or current density, then we get this. Then we can rewrite a little with the help of our field equations and we get this. What we see here is the wave equation for a transversal electromagnetic wave with a source term. And the source term we can see is the time derivative of the gradient on the electric time component. This means that if we can introduce this quantity, then we can generate photons of light. And because the electric time component is coupled to the gauge wave field, a gradient in the electric time component will work like a converter that will convert gauge waves into photons. To engineer this condition, we look at the second field equation. It has three terms: a rotation on the magnetic field, a time derivative on the electric field, and a gradient on the electric time component. When we start, they are all zero. First, we generate a changing electric field vector. This will induce a rotating magnetic field. As the changing electric field disappears, the rotating magnetic field will induce a gradient of the time component. This picture shows a sketch of the setup. We have two magnets pointed against each other. They are used to feed the rotating magnetic field so it doesn't die down. Then we have the two ring electrodes to generate the changing electric field. The idea is to induce a stable rotating magnetic vortex that generates a gradient in the electric time component. To convert gauge waves from the sample in the sample holder. When the gauge waves are converted to light, they are recorded with the camera. Here to the right is a picture what our prototype instrument could look like. The whole setup should be put into a cryostat to avoid thermal noise. So right now we are looking for funding to develop the first prototype and start pilot experiments. We are at the conclusion. Gauge waves theory is a new theoretical framework, so there are still a lot of open questions, like does other gauge fields have gauge waves? How are other particles modeled in gauge waves theory? Given both quantum mechanics and gravity seems to be two sides of gauge waves theory, will it lead us to understand quantum gravity? Gauge waves theory eliminate the point particle paradigm known from quantum mechanics. Will it also eliminate the singularities known from general relativity? Only 5% of the universe is visible to us. If the quantum lens can help us uncover just 5% more, then we have already doubled what is visible to us. And there is no way to know what we will be able to discover in that part. The quantum lens have other potential use cases apart from space exploration. There's also debugging of quantum circuits, studying quantum biology, exploring material science, and make energy optimization, and probably many more. Here is a list of references. If you have enjoyed the subjects in this video and you want to dig deeper,